Okay. This is part of the class. We have extended homework due tonight. As I mentioned, if that creates undue hardship for you, let me know, since it was my fault. I'm especially understanding about extensions, working with you, making sure you get it in and it represents the best of your ability. There's also the new homework that's been posted that is due on Wednesday. I'm sticking to Wednesday because I want to get it turned around to you by Thursday so that we can take an exam on Friday that has to do with some of that material. I am only slightly starting to regret not having a final because then I could push it a little bit and just push some of this stuff to the final, but I did not do that. And I don't think people want a surprise final at this point. I'm not gonna do that.
For the last assignment, though, never do on like Friday.
Yeah, we do the last day of class or something that works for people. So last time we were in the process of coding up our heap. We said we had 3 fields. We have the elements that we're going to store, the size, the capacity. The capacity is kind of just the length of elements. So all we've done with the capacity is really saved elements.length wherever we use capacity. So that's up to you as to whether you think that's a good design decision or a bad design decision. We had a couple easy methods, size and is empty. We did insert, which is going to throw an exception if the heap is full. Then it's going to insert that data at the last position in elements, and then we need to heapify it up in the heap to where it goes. So we coded up the heapify up procedure that just loops and compares the parent to the current, which is the thing that we just inserted. So that's going to take that and kind of work its way up to where it goes. Then we started remove. If the heap is empty, we can't remove. Otherwise, we're going to extract the root, which is going to be the element in position 0 in the array. Then we're going to swap that to the last position so that we can delete it. We did that by setting elements of that last element to null, decrement the size, and now our root is not going to be where it belongs, so we need to down heapify that. So what's left for us to do is basically implement down heapify. And that should basically be everything that we need, except maybe a 2-string. And then we can move on to talking about heap sort and how heap sort works. It should be pretty easy to implement with everything that we have here, all of our tools. So let's just start in on down heapify. So what do we need to do? What should we start out by initializing? What do we need references to? Because we're going to be looping this procedure, we're going to kind of need some nodes, and then we're going to need some nodes, and we're going to need some nodes as we heapify down.
Heapify, heapify, that's when we switch the root small, right?
Yeah, I said heapify up and down heapify. Let's keep this, let's call this heapify down and stays consistent. So
And usually it's not to store the root, right? And then it's.
yeah. In general, though, is it gonna continue to be the root, or what could we call that? That would,
Like the parent.
yeah. So let's make a int parent index. We're gonna set to be 0. It's gonna represent the root. What else do we need access to be able to make the first decision about, do we swap the root with something? Left child and right child. So sure, let's store the left child. What was the position in the index of the left child?
Times correct plus one.
In general, it would be 2 times the parent plus 1. Parent index. And the right child is going to be 2 times the parent index plus 2. We probably use hard code them at the moment, and then just make sure that if we're going to do this in a loop, that we're going to figure that out. So we also need some way to go get and figure out which of these children is the smallest child. Since this is a min heap, if we're a max heap, we need to find the largest child. Since this is a min heap, we need to find the smallest child. So let's go try to find the smallest child. And I think that that process, we may want to make our own method for, because we're going to be doing it a couple times, once initially and once in preparation for the next pass through the loop. So let's say what do we want to call this? Select smallest child. And then we want to pass in the left child and the right child, and it will return to us whichever one is the smallest child. That will be the process that we want from this. So we're going to put heapify down on hold for a moment, and let's make sure we write the correct logic for select smallest child.
And that returns the index of the smallest child.
Yeah, we'll return the index of the smallest child. So let's say this is going to be, actually it should really be private. We don't want the user calling this for some reason. It's going to return an index. Select smallest child. And we're going to pass in a left child and a right child. All right. How do we do this? How do we figure out which of the 2 children is smaller? So this is making some assumptions. Are we guaranteed to have both a left child and a right child? No, we're not. So we need some extra logic in there to make sure that we have that. So we could do something like, the other thing that we could have is if for some reason we're out of bounds, the left child could be the largest possible value and the right child could be out of bounds. So let's first do a check and make sure that we're in bounds. And the reason for this as well is that we could go to a leaf, and if we try to select the smallest child of a leaf where both left child and right child are null, then that's not great. So let's say if either left child is greater than or equal to capacity, I think that identifies one of the cases. The other case is that elements of the left child is null. If that's the case, we need some way of representing failure. Since we're returning an int, what is an int that could never be returned from this function? -1, that's a perfect value to use. So we're going to use -1 to represent failure. If this function returns -1, then something went wrong. Or that should be what terminates a loop in the heapify down procedure. All right, that sounds good. So Afterwards, we should probably check and figure out what is the case in which we want to return the left child. So we can identify if elements of left child is, well, we don't know, we can't say greater than or less than at this point because these are t's. So we want to compare to elements of right child. And that has to be what? Should that be greater than or equal to 0, less than or equal to 0? What would make us want to return the left child from this?
So left child is less than.
Yeah, so less than or equal to 0. I would say it's okay if they're the same. We'll return the left child in the. There. So if that's the case. Great. I feel like there's one more case. Right child is null. The right child is null, and we want to return the left child because the right child doesn't exist, so. That would keep this from returning that. I think that'll work. If that's the case, then we return the left child. If we follow through all of this logic, we don't need an additional if statement, we'll just by default, yeah.
Just if we were did the compare to and elements right child was null, would it return something in the compare to?
How does compare to work with null? I actually don't know that off the top of my head. So actually that makes me want to switch these. So why don't we do that? Why don't we check the right child for null first? And we can use short circuit evaluation. Have I talked about short circuit evaluation in here? So if we have an OR and the first element ends up being true, then true or anything is true. So it does not run the right half of the Boolean expression. So if we check for null on the left-hand side and then dereference null on the right-hand side, that's fine. Because if it happens to be null, we'll short circuit evaluate and not dereference. Does that make sense? It's the same thing with and false. If the first part of an and is false, then the second part is not checked. Because false and anything is false. So now it doesn't matter what the compare to does with null because we will never run the compare to with null. That doesn't mean I shouldn't look it up, but for the sake of time. Now, by default, I'd already done this. By default, we can just return right. We fall through both of these if statements, we can just return the right. Questions on select smallest child? I think this should work. All right, we're gonna go back to heapify down, and we're going to assume that smallest child now contains either the left child or the right child, whichever one is smaller. What should we do next?
We check the smallest child is less than 0.
We can definitely do that. So we want to probably do something about a loop. So while something is true, we want to continue setting up and swapping the parent with the smallest child, parent with the smallest child, parent with the smallest child. What is the condition that would tell us to stop? That's actually checked in select smallest child. So this error case is gonna be super useful to us because it tells us to stop this loop. So while smallest child is not -1, continue and do something. Because these are the two error cases that would tell us that we're done.
Then that essentially tells us that we've reached LD.
Now, we don't know we're going all the way to a leaf necessarily. But. That would be the case if elements of left child was. I think this will work. So what do we do inside of this loop? How do we go about it? We want to first do a swap. Because if the selection is valid, then we want to swap parent with the smallest child. So we already wrote a swap. It takes in a child and a parent, and it doesn't matter which order is, just does a swap. We just called it child and parent, but it doesn't really matter what that is. So let's swap the smallest, swap the parent with the smallest. I said child first, right? So I guess smallest child and parent. It does not matter the order we do this. Parent index, that's what I call that. So we'll pull off the swap. How do we prepare for next time? The new parent is what? Parent index.
The parent's the child.
Yeah, it's the smallest child. What's the new smallest child?
We call us like smallest child.
Yeah, we're gonna borrow exactly this logic and select the smallest child again. And note that left child, now that we've changed the parent index, we didn't hard code this. So left child and right child. Are they changing or do we need to modify them? You don't need to redeclare them. All right, what do we think about this heapify down? Is it gonna work? Heapify it?
I'll find out.
One way to find out. So let's come up with some kind of test case. And we probably want to have a 2-string. So that we can actually verify what the internal state is. Let's have some fun with this. We want to see quite possibly the longest line of Java that you've seen so far.
Sure.
All right, let's return arrays dot, it has a stream that gives you a iterable stream of the elements of that collection. So we want to pass in the name of the array, which is elements. We take that, and once we get that stream, we want to remove all nulls from it. So that we don't see any null elements that have been instantiated. So you can filter or dot filter the stream. And you want to filter such that element arrow element not equal to null. It's all elements that are not equal to null. Dot collect,
I have a question.
yeah,
So inside of the filter, they have like the two predicate objects, so one says objects non-null, and one says object is null. What is that?
what inside of here, you mean?
Yeah, so like if you were to like copy that and then delete that inside of filter and type in null, they'll come up with, or I guess maybe not in Eclipse, but in IntelliJ, it comes up with two options and it says objects, or objects and then non-null and objects is.
I think it's overloaded. Basically, you can select those that are null or those that aren't null. So we want all elements that are not null in our stream.
So would non-null do the same thing as that?
Possibly, I am actually not familiar with that version of it. I'd have to play around. Type it out, let me know what happens. So we're going to collect all of these together. And that collection needs to be a list. So to get it to be a list, we need to say collectors.toList. And then all of this is a list, not a string. So we need to convert this list into a string. So we call dot, I think this is outside of this one, dot toString.
What does the arrow do in the filter?
All elements such that the element is not null. Think of it as a such that. There are plenty of other ways we could do this, but I figured, why not show you the worst side of Java? That's a class. So a collector is an interface that allows you to have. So accumulating elements into collections. So we're gonna make a list out of a bunch of elements. So this filter creates elements that aren't in a particular form. So we want to take all of these elements, put them into a list, convert that list into a string, return that. So very long, but I think it will work. All right, so now if we have a way to visualize this, we can at least say, all right, we want to make a heap and make sure it is legal. So let's make a new heap. How did we say we were making a heap? It's a min heap. We said we can give it a size. 500 is plenty of elements. We're not gonna need more than that. So we can heap dot, and now we can start to do things like insert. But a min heap needs a type, so let's make this a type integer. And I know that I've typed out the integer here before. If you leave this blank, Java just autofills it with whatever this happens to be in most cases. If you ever get something where a time where it can't figure out, there's an ambiguity, you can just type it in. So heap dot insert. We now give it an integer if we want to insert in some order that is going to not be a legal min heap. Let's just insert 5, then I'm just gonna down to 1. There. Five, 4, 3, 2, and 1. We probably throw that into a loop. Now we want to print. Heap.toString. And see if insert works. We have 1, 2, 4, 5, 3. Try that. So 1, 2, 4, 5, 3. 1 is bigger than 2 and 4. 2, sorry, smaller than 2 and 4. 2 is smaller than 5 and 3. Seems like a legal heap. So we could draw that out as a tree form.
Is that in order? How did
It's in level order.
level order?
Yeah. It's printing out basically the contents of the array. And the array is stored in level order. So yeah, we have the root is 1, the root's children are 2 and 4, so that's a legal subheap. And then 2's children are 5 and 3. 4 does not have any children. And that way you have the fewest number of levels and the last level is all the way to the left. So now we can remove. Heap.remove. We don't need to store that value, it's gonna return the 1 to us. But it should be swapping the 1 with the 3 and then heapifying down the 3. So if we again print out the heap.toString, we should get another legal heap. All right, 2's children are 5 and 4. And 5's child is 3, that is raw. So there's an issue with remove. I'll figure out what that is offline. I don't want to go through a 10-15 minute procedure. Instead, I want to talk about how to actually go through the heap sort procedure, but I will figure this out. We'll come back to it. So imagine that we wanted to be able to sort a heap. Or sort an array via using a heap. This isn't gonna work because the heap doesn't work, so I won't be able to demo it, but it should be fairly straightforward. In addition to a main, I'm gonna make a new static function. And this is. We don't really need to return the array that we're gonna use, so this can be a void, we'll call this heap sort. And it will take a array of type T that we'll call array. And the goal will be to sort this with some kind of with an actual heap structure. T is non-static, of course. Let's just heap sort an integer. That's perfectly fine. So now we are going to take everything from this array, put it into a heap, remove it from a heap back into the array. So how could we do this? I guess I can show you the slide that tells us this. So here's the heap sort slide. I don't think I actually went over this. So heap sort is just the process of taking a list of some kind, putting everything in that list, inserting them one at a time into a heap, and then removing them one at a time from a heap and putting them in the appropriate place in the array. So the entire reason that I implemented a min heap is so that we can fill the array from left to right rather than from right to left. So thinking about the actual time of this, how long does it take to put everything into a heap? The insert procedure took how long? Log n, since there's at most one swap for each as we heapify it up. There are n elements that we're inserting, so that entire process is n log n. Once they're in a heap, we can then remove the either largest or smallest element. That is constant time. The down heapify process takes log n. And then there are n of those to do as we go take out n elements from the heap. So that's also an n log n procedure. Since we do them sequentially, we do the insertions followed by the deletions, we add those running times, n log n plus n log n is big O of n log n. So we have another efficient sort. I would argue that it's probably not quite as efficient as merge sort or quick sort, probably about twice as slow. But it's still going to scale significantly better than any of the sorts that we saw at the beginning of the class. So this is why it's not the default sort, but it's a pretty easy sort to implement if you already have a heap structure. So we would say for integer I in array, we want to, we should probably make a heap first. In fact, I can just copy this. One change I want to make to it, and that's that I don't want to set it to be 500. I want it to be array dot size. It's not a, it's a dot length because it's a standard array. So for each integer in the array, we want to insert that value.
Can you kind of talk about the enhanced for loop, just briefly?
Yeah, this for each loop.
Yeah,
So the for each loop just basically says for every. We already know how long the array is, so this is basically equivalent to saying for int I equals 0, I is less than array dot length I plus plus. Since we don't actually use the I, the actual counting variable in this, we would have to do something like, say, heap dot insert array of I. Because now we use the index into it. So this is just saying, rather than storing the actual I value and caring about where we are, we'll just say for every one of them. And the compiler figures out how many there are. And this is actually using an iterator underneath the hood, which is why I wanted to start the class by talking about iterators. For each loops, use an iterator underneath the hood to be able to go through and say, for a collection that is iterable, do this has next loop that goes through and grabs each element. And then does something with that element for each one of those elements. So yeah, whenever you have a collection, you can use a for each loop as long as you're doing everything in the collection.
so if you have, so basically the main difference is that in the regular for loop is that you're gonna use the I inside of the loop, and then for the for each loop, you're never gonna use the I.
Right, we don't need, I now represents the actual value of the integer, not the integer's location in the array. So since we don't need that, we want to do the same thing to every element and not something that depends on its location in the array. You can use a for each loop. It just says grab the next one, do something to it. Grab the next one, do that same thing to it. Grab the next one, do that same thing to it. In this case, that thing is inserted in. We don't do something different to the 50th element than we did to the third element. We're still inserting it into the. So it's equivalent to the lower loop. It's just a little bit less psychic. Any questions about 4-inch loops? Sorry, I kind of assumed that people had seen them in 211. And if you had not seen them in 211, it probably looks a little strange. We did. Alright, so now we have this, and now we want to basically remove everything from the heap. So we can say. Now we actually need some kind of counting variable, because we need to know where to put it in the array. So. Let's start an index out at 0, the place we want to put it in the array. And then we can say, basically, while the heap is not empty. We want to remove into that index. So we want to say array of index gets heap dot remove. Since we know we're removing the smallest element. When we remove the very first element from this, it goes in position 0 in the array. That's going to be the smallest element of the entire array. When we remove it next, we should bump up index before we talk about that. The next thing goes in index 1, the next thing goes in index 2, the next thing goes in index 3. For each remove, we're removing the smallest thing that is left in the heap. So if we do this procedure n times, we could also use a for loop that does this for array.length times, because we know exactly how many elements are in the heap. So either way you do this would be fine. But we just refill the array. And now, whatever array we passed in, by the time we reach the end of this while loop at the end, it's sorted. Assuming that my heap is implemented correctly, which I will go fix and talk about. Anyone have questions about heap sort? Because this is quite a small amount of code, assuming you have a heap structure that just already has the insertion and removal functions made for it. This is a very little amount of code, and I find it to be pretty straightforward compared to something like the implementations of merge sort or quick sort. Yeah.
Essentially, the difference if you had a max heap is you would want to start at the end of.
Yeah. Yep. So that is one thing that I want to talk about is what changes would we need to make to these concepts if we did have a max heap instead of a min heap? What would need to change?
All the comparatives.
Yeah, comparatives would be flipped. Anything in insert and heapify up? So this comparative should be greater than 0 instead of less than 0. That's basically it, huh? There's not much in here that actually has to do with the larger versus smaller that isn't directly a comparative. So that's really why it's only worth implementing one of these, because the other one is so incredibly similar. So yeah, this is basically what I wanted to show with regards to heaps and heap sort. Obviously, I would prefer it to be working so that I can show it to you, but I'll do that at the start of tomorrow's class.
You need the post.
Yeah. Yeah, if it's not up when you're looking for it, let me know and I'll get it up. I think I have a few lectures, the last few lectures to post as well. I've been behind on my lecture posting.
What's the dog that bugs in the remove function or method?
Yeah, it's definitely in there somewhere. In either remove or heapify down. I'm guessing it has to do with that this is not a valid comparator. That's my guess. I would want to play around with that first, but I'll debug it and we'll figure it out. All right, we have 10 more minutes, so I'm gonna go through a little bit more stuff after heap sort. So we talked about heap sort, which is really just taking an array and inserting it into a heap, and then removing it from a heap, which kind of seems like a total waste, but hey, it sorts and it sorts efficiently. And thinking about just how inefficient that feels to you. The basic sorts that we talked about at the beginning of the class are worse than that. Worse than just taking every element of the array, inserting it into a heap, where each one has to do a logarithmic amount of work to bubble, and then removing, where removing it's also creating a bubbling. Yeah, the basic sorts are very inefficient. So we have implemented now. And we're gonna be moving on to talking about how we can use heaps and how we can use the hash tables and trees that we've seen to go back to and learn about some additional data structures that actually use these structures as their underlying structure. Anyone have any questions about the implementation of heap sort? So we did all this. Let's talk about how we can use some of the stuff that we've talked about. So we've seen hashing, we've seen trees, and now we can look at how sets are actually implemented in languages. We talked about sets quite some time ago at a very basic level, because here's what we'd like to be able to implement. But it turns out that we want a set to be efficient. And so we need a set to have efficient insertion, efficient deletion, efficient union, intersection, and difference. We talked about needing to have an add all. If you have a union and you add all of one set into another set, then you end up having a union, right? You have everything that's shared in common between, not shared in common, everything that's in one set or the other set or both sets, since sets can't store duplicates. Intersect is going to use a retain all method that says you pass all of the elements from the second set onto the first set, and the intersect is just the retention of everything that is in the second set that was also in the first set. That's the definition of set intersection. So retain all is the implementation of set intersect. And then difference is going to use remove all, where we want to talk about the difference between what's in the first set and what's in the second set. So we're going to remove everything from the second set from the first set and see what's left over. And that gives us the definition of set difference. So we don't actually need a union method, an intersect method, and a difference method. They use three built-in methods: add all, retain all, and remove all. So if we use an underlying list, an add all, a retain all, or remove all are all either going to be linear or quadratic. Think about add all and implementing add all in a list. What does that look like? For each element that we have to add, since it's in a set, is there an easy structure for something like a find? Remember that in a tree or a hash table, find is either constant or logarithmic. It's constant if the hash table size is small enough to where we know we're going to have a constant amount of work to do to locate. We look at the hash, we do the hash function, we go find where it's stored, it's there. Or there's a single collision and it's in the next place we look, rather than a proportion of the table size. With a tree, a find is going to do a comparison because it's stored in order, and it's going to say, is it less than or is it greater than? And you can remove half the tree each time. So find is going to be logarithmic in the worst case. But if you don't store these in some kind of order in just a list, we have to look over the entire list to try to find it, which is going to be proportional to the length of the list. So a single add, well, maybe it's constant to add at the end, but it's going to affect find afterwards. Something like retain all, where we're trying to locate and find each element in an array. Now we have something that is linear for each element that we need to attempt to retain. So we end up with something that's quadratic based on the size of the second set. Does that make sense? So it's highly inefficient to use a list for these things. Same thing with remove all. We actually have to go find it so we can remove it from the first set. And if we go find it, we have to go do a search element by element down a list. So it doesn't make sense to implement a set with a list. It just doesn't. It's highly inefficient. So if we use a hash table, every one of these operations is straight up faster than its list counterpart. If we need to be able to compare elements for some reason, using a tree, all of these operations are faster than using a list. So because of this, it's significantly better to store a set in either a hash table or a tree than it is in a list. Which is why it's done the way that it's done. But now let's think about just how much faster these are in a hash table or in a tree. And so I have this nice built-in structures comparison for the 3 different ways that sets are actually implemented. There is a tree set, a linked hash set, and a hash set. These are the 3 concrete classes that you can instantiate if you want to store a set in Java. So a tree set uses a built-in tree object. A hash set uses some kind of probing, either quadratic probing or more intelligent probing, and a linked hash set uses a linked list. So we've talked about the 2 different ways to hash, and now you have total control over what you instantiate. You instantiate one that uses collisions and probing, or collisions and a linked list as the way of storing that set. So this tells you kind of the difference here. So the tree set, even though a set doesn't care about things like order, it does have an underlying order, and that order is in sorted order. If for some reason it makes sense to compare these objects to each other, and you know that you're going to be accessing those objects in a certain way where that might be more efficient than searching via probing, then you can use an underlying tree object, and that will end up having better performance than the hash set. But the general go-to for you should be a hash set. The hash set by itself, in the generic case, is going to be the fastest object here. There just might be some instances where it makes sense to store them in a tree. So the underlying data structures, we have a hash table, doubly linked list plus hash table, and a balanced binary search tree. I have not had time to go into balanced binary search trees, nor will I. That's going to be an algorithms topic. So if you take 320, you will actually write your own red-black tree to balance a binary search tree, which actually makes sure that you get that logarithmic behavior out of a tree. For all 3 of them, doesn't allow duplicates. You would expect that out of a set. We did talk about how trees can support duplicates. The way that the tree set is implemented, there cannot be duplicates. And the same thing for hash tables. You can have duplicates in something like a linked hash set. It would be possible to code it that way, but the linked hash set looks for it and does not insert duplicates because it's meant to store a set that doesn't have duplicates. So the fastest performance overall is the hash set, as long as the table doesn't get too full. But the hash set will resize for you if the table does get too full. You don't have to worry about it. So just knowing what it's doing underneath the hood is very good for being able to identify when to use the object correctly. But you don't really have to worry about implementing it yourself from here on out. There is something built into Java that just lets you make a hash set. It has the implementation and all of the math that we have talked about. So you can just use it. We talked about iteration order, or we can talk about iteration order. But one of the downsides of using a hash set is we don't know the order that elements were inserted into the structure. A linked hash set keeps track of that. Because it's a linked list, the order of the linked list of everything that maps to the same position is gonna tell you the order in which they were inserted. And tree set is of course sorted based on some kind of natural ordering based on the compare to that it uses to determine less than or greater than, that's necessary as part of making a binary search tree. So if you can't compare the objects that you're trying to make a set out of, then you cannot use a tree set. It extends comparable, so if you can't have comparable objects, then you can't use a tree set. If you have multiple null values, you want to use a hash set. If you have any ability for anything to be null, then a tree set obviously is not what you want. A single null value is allowed in a linked hash set. So we'll come back to this and we'll talk about maps tomorrow as well, and then we will start to talk about graphs as the last major topic that we're going to talk about in here. So I will see you tomorrow for that.